Hello everyone. Today our topic of discussion will be diagonalization. But before we head ahead into more details, let's look into some of the basics of it. So at first, let's discuss what is identity matrix. So identity matrix is a matrix that has all zeros except in the diagonal it has only ones. So as you can see over here, in the diagonal it is only ones. That's a 2 by 2 identity matrix. If you have a 3 by 3 identity matrix, it will have again in the diagonal all ones and the rest of all the elements will be zeros, and so on. If you have a 4 by 4 matrix, you'll have 4 rows and 4 columns, but the diagonal will be all ones and the rest, all the other elements, will be zeros. And here are two facts about it. That is, if you have a matrix A and you multiply it to the inverse of A, you will end up with the identity matrix. And the same goes for if you have A inverse multiplied with A, you will end up with the identity matrix. So identity matrix could be written as I, or it could be even written as IN. They are the same thing. And next we'll discuss diagonal matrix. So a matrix A is called diagonal matrix if entries outside the main diagonal are all zeros. So as you can see here, the diagonal elements here are non-zero elements, but the rest, all the elements, are zeros. So such a matrix is called a diagonal matrix. So you can say that an identity matrix is also a diagonal matrix. So I hope that makes what is a diagonal matrix clear, because when we want to go deeper into diagonalization, you should remember that everything in the diagonal, or all the elements in the diagonal, should be elements or non-zero elements, but the rest of the elements in the entire matrix should all be zeros. Now here we have the definition for diagonalizable matrix. So when is a matrix diagonalizable? So here you have an n into n matrix A is called diagonalizable if there exists an invertible n into n matrix P such that this condition applies. So a matrix A is diagonalizable if there is another matrix P that has an inverse. So that should have an inverse, right? And then you take the inverse, multiply it to the matrix A, and multiply it to the matrix P itself. That will end up giving you an n into n diagonal matrix. So we just discussed what is a diagonal matrix, which means that all the elements in the diagonal will be non-zero elements, the rest are all zeros. So that's the condition that says if a matrix A is diagonalizable or not. So here we have a remark, that is, an 2 by 2 matrix A with elements x, y, z, and gamma is diagonalizable if there exists an invertible 2 by 2 matrix P such that its inverse times the matrix A times P is equal to a 2 by 2 diagonal matrix. So let's look at an example here. This is a general example with alphabets. So if you have P written as A, B, C, D here, and it is invertible, which means it has an inverse, and its inverse would look something like this, where the denominators are the determinant of P. So you have A times D minus C times B. So that's the determinant here. Everywhere down here is the determinant of P. And above you have the elements, that is, they're exchanged kind of here. So the A comes below and the D goes above. So that's what is happening here. As you can see, the D is here and the A is down. And the signs of these two elements changes. So if it's positive, it becomes negative. If it's negative, it becomes positive. Here, B and C are both positive, and therefore they have become negative C and negative B. They don't change position, only changes the sign. Okay, so that's how you find out an inverse. And then after you get the inverse, you can take the inverse multiplied with A and the matrix P itself, and you will get a 2 into 2 diagonal matrix. So it is the same as saying here you have the P inverse times the matrix A times the matrix P, and when you multiply them you get a diagonal matrix where the diagonal elements are non-zero elements and the rest of all the other elements are zeros. Okay, now here we have a remark which says that if you remember, yeah, here the P, the elements are A, B, C and D. So if your vector AB is an eigenvector and your vector CD is also an eigenvector of the matrix A to two different eigenvalues, R1 and R2, then you can say that the matrix A is diagonalizable. Why it would be diagonalizable? Because this condition is true in that case, right? So which means that P is invertible if both of these eigenvectors, that is, this is an eigenvector, this is an eigenvector. So let's say this belongs to the eigenvalue R1 and this belongs to the eigenvalue R2. And if these two eigenvectors are corresponding to two different eigenvalues, in that case P is invertible, and in that case this condition will also be true. Now if you remember our last tutorial, in that tutorial I told you that if we have two eigenvectors to two different eigenvalues, they cannot be on the same line, right? But okay, let me draw the graph to make it more clear. So let's say we have here an eigenvector which is 3, 2 or 3, 2. So if you have one more eigenvector which is on the same line, let's say it is R times 3, 2, which you can say as 3R 2R. In that case, if you have your P will be now 3, 2 and 3R 2R. And to find out the P inverse, we first need to find out the determinant of this matrix. So what would be the determinant of P? It would be 3 times 2, that's 6R, minus 3 times 2, 6R. And that is equal to 0. And if the determinant is equal to 0, then P inverse is not possible, right? So that's the reason why it said that you cannot have two eigenvectors to the same eigenvalue, okay? Because then it will be on the same line. Or even you cannot have two eigenvalues to the same eigenvector. In that case also it will be on the same line, as I showed you in the last tutorial. So in both the cases it would be on the same line. So only this case here applies, that is, you need to have two eigenvectors to two different eigenvalues so that they are on different lines. So let's take another eigenvector here maybe, and this one is minus 2, 1. So now we have two different lines, two different eigenvectors to two different eigenvalues. In that case our P is 3, 2 minus 2, 1. So the determinant of P will be 3 times 1 is 3 minus 2 times 2 is 4, that's minus 4, which is equal to 7, and that is not equal to 0. So if the determinant is not equal to 0, it means that you can find out the P inverse. It's possible to find it out, because if you remember, I just showed you here to find out the P inverse, you need to find out the determinant, right? You need here the determinant. So yeah, once the determinant is not equal to 0, in that case P inverse we can find it out, and therefore this condition can also be applied, and therefore the matrix A is diagonalizable. So it's all connected, right? So just remember that your two eigenvectors should be in different lines, not on the same line. Therefore they will be corresponding to two different eigenvalues. Therefore R1 is never equal to R2. They're never equal to each other, your eigenvalues, and that's it. Those are the conditions for having or for being able to make A diagonalizable. Okay, now let's go ahead to solve today's question. Our question for today is, show that the matrix A is equal to 3 minus 1 minus 8, 5 is diagonalizable. So we have to show that this matrix here is diagonalizable. So if this matrix has to be diagonalizable, in that case we know that it needs to fulfill the condition, which is P inverse times the matrix A times P should be a diagonal matrix, right? So if we have to show that A is diagonalizable, it should fulfill this condition here. So for that, let's go step by step. So our first step, let's say step 1, should be to calculate the eigenvalues of A. So the first step is to calculate the eigenvalues of A here. Now, how do you calculate the eigenvalues of A? You have to take the determinant of the matrix, but you have to subtract lambda from the diagonal. That's 3 minus lambda and 5 minus lambda. The rest of the elements stay the same. And determinant of this matrix here will be 3 minus lambda times 5 minus lambda minus 8 times minus 1 is 8. And now if you open the brackets here, you will have 15 minus 3 lambda minus 5 lambda plus lambda squared minus 8. And okay, I had done a small mistake here. I shouldn't write this here down. So yeah, let's put it here. And the determinant of this should be equal to 0. That's how you get the eigenvalues. So here we'll have these equating to zeros. So now here minus 3 lambda minus 5 lambda. Okay, first let me bring the lambda squared in the front, and then here we have minus 8 lambda, and 15 minus 8 is plus 7 is equal to 0. So now we can use the quadratic formula. So here you have, let me write it as lambda 1 comma 2, because it's a quadratic formula, so of course we'll have two solutions. Therefore here we'll have two eigenvalues. So here we have 1 comma 2 is minus b, so minus 8 is 8, plus minus square root of b square, that's minus 8 squared is 64, minus 4 ac, 4 times 1 times 7, that's 28. divided by 2a, so that's 2 into 1, that's 2 here. And so if we solve this further, we'll have here, or let's go ahead and solve it straight away. So here we have 8 plus minus square root of 36 divided by 2, and that is equal to 8 plus minus 6 divided by 2. So your lambda 1 is equal to 8 plus 6 divided by 2, which is 14 divided by 2, that's 7. So we have got our lambda 1 here, and lambda 2 is equal to 8 minus 6 divided by 2, that's 2 by 2, which is equal to 1. So we just got both our lambda values. Lambda 1 is 7 and lambda 2 is 1. Now let's go to the second step. So our second step here, step 2, is to calculate the eigenvectors corresponding to the calculated eigenvalues. So we have to find out now the eigenvectors for the eigenvalue 7 and eigenvalue 1. So let's start with eigenvalue 7. So in that case now, we know that if we take the matrix A and we multiply it with the eigenvector corresponding to 7, so that's, let's say it's AB, is equal to the eigenvalue times the eigenvector AB here. So we can get the eigenvector from this. Now let's solve it further. Here we have 3a minus b is equal to 7a. And then here we have minus 8a plus 5b is equal to 7b. Now, if you solve that one more step further, you get here, if you take the 7a to the other side, you get here minus 4a minus b is equal to 0. And here you will get minus 8a minus 2b is equal to 0. Now, if you solve that one more step further, for both of them, you will get your b is equal to minus 4a. Okay, so we just got the value here. Now, with this value, we can find out the corresponding eigenvector. So the corresponding eigenvector here will be eigenvector here. Eigenvector will be, for A we got, let's take A as R. In that case, B will be minus 4 times A, so it will be minus 4 times R here, where R can be any real number. Okay, so here we have, we can check this out except 0, because if R is 0, then this will not be an eigenvector, because eigenvector has to be a non-zero vector. But if you put R is equal to 0, then the whole vector is 0 vector. Okay, so we can check this out if our eigenvector is correct or not. Let's check. So let's take the matrix A, that's 3 minus 1 minus 8, 5, times the eigenvector R times minus 4R, and that will give us here 3 times R plus 4 times R, and here we have 8 times r minus 20 times r. So that is equal to 7r minus 28r. Now if you take out the eigenvalue as common, you get here r and minus 4r, which is our eigenvector. So that satisfies what we just wrote here, right? So we just check that the answer is correct. Now let's go ahead and work for the second eigenvalue, which is lambda is equal to 1. So again, we take our matrix A, that's 3 minus 1 minus 8, 5 times, let's say the eigenvector now here is CD, is equal to the eigenvalue times the eigenvector CD. So this gives us here 3C minus D is equal to C. And here we have minus 8C plus 5D is equal to D. So solving that here gives us 2C for the first equation. Here we have, if we bring the C on the other side, we have 3C minus C, that's 2C minus D is equal to 0. And for the second equation here, we have D, if we bring it on the other side, we have here minus 8C, 5D minus D, that's plus 4D is equal to 0. Solving that again, we get here D is equal to 2 times C, and that's for both of them again. Now for this, let me squeeze the information here a little bit so I have more space. Okay. Okay. All done. So let's go ahead and write down the eigenvector now. So the eigenvector here now will be, for C, we'll keep it as M, and then D will be 2 times M. So it's 2 times M, right? So that's the eigenvector. M could be any number again, any real number except for 0. And again, you could check it here using the matrix A, that's 3 minus 1 minus 8, 5 times M and 2 times M, and that would give you the eigenvalue 1 times M times 2M. So this you could check it yourself. And now let's go ahead and do our third step. So step 3 now will be to choose 2 eigenvectors. We'll choose 2 eigenvectors AB and CD corresponding to the eigenvalues. Okay, so we can have for the first one, for AB, as we know it, we have the eigenvector as Rn minus 4R. So what we could do is we could take for R1. In that case, we'll get here, if R is 1, and here it will be minus 4 times 1, that's minus 4. So you can say that this is chosen from eigenvector R minus 4R, and here we put the value R is equal to 1, right? Now, if we take the next one, that is M and 2 times M. So again, I could choose M to be 1. In that case, I would have here 1, and 2 times 1 is 2. So I can write it again here, chosen from eigenvector M to M, and here we put R is equal to 1 again. But you could put any R and you would get here any 2 eigenvectors, right? Because as I just told you, R could be any real number, so you could just choose your own, anything above 1 down 2, maybe anything that you like, right? So maybe I'll just show it to you in the next step. So let's go to our step 4 now. So we go to step 4, that is to determine matrix P is equal to A, B, C, D. So we just saw matrix P, and now we'll determine our matrix. So as we can just see above here, we just decided already. So here we have A, B, C, D. And we just chose AB to be 1 minus 4 and CD to be 1, 2. Now you could choose this as anything, right? So you could choose this, let's say, I'll just do some for example. So here P could be, let's say we choose P to be, okay, let's put here the value of R to be 2, and here the value of M to be minus 3. So here then we would have here R is 2, 4 times 2 is 8, and M is minus 3, and 2 times minus 3 is minus 6. We could take P as 2, 8 minus 3, 6, minus 6. Or you could also take, let's say, R, let me choose now as, let's choose the second R. Maybe I'll do the different colors so I don't need to erase it. So let's say for the second R, I choose it to be minus 1 here, and M to be, let's say, half. In that case, P would be minus 1, and here would be 4. And then we would have here minus, sorry, not minus, half here. M is half, and half times 2 would be 1. The P could be even like this. So P could be anything. Infinite number of values it could be, right? So as you wish, you can choose and you'll still go to the right answer. Okay. So yeah, let's go ahead now to step 4. Sorry, step 5. So step 5 is to determine inverse matrix. inverse matrix of P. Okay, so how do we get the P inverse? We know that we have to, let's write down P at first before we go on to its inverse. So P, as we just chose before this, here we chose P to be 1 minus 4, 1, 2. So here we have 1 minus 4, 1, 2. So P inverse will be 1 over determinant of P, right? Times, you will have here these two values exchanged in the diagonal. So 2 would go up and 1 would go down, and the other two values sign will change. So plus 1 will become minus 1 and minus 4 will become plus 4. Okay, now what is determinant of P? Let's find out separately that maybe. So determinant of P is 1 times 2, that's 2, minus 4 times 1, so that's minus 4, and minus 2 plus 4, that's 6. So determinant is 6 here. So in that case, we would have here 1 over 6 times 2 minus 1, 4, 1. And that is equal to 2 divided by 6, 4 divided by 6, minus 1 divided by 6, and 1 divided by 6. Okay, so that's our P inverse. Now let's go ahead to our last step, step 6. So here we check our equation. So here we check the equation that we talked about at the very first here. So we had here P inverse times A times P will give us the diagonal matrix, which had diagonal matrix with eigenvalue 1 and 0 and 0 and eigenvalue 2. So here that means your P1, which we just wrote down, it was 2 divided by 6 here, 4 divided by 6, minus 1 divided by 6, and 1 divided by 6 times A, which is 3 minus 1 minus 8, 5, times P, which is 1 minus 4, 1, 2, will be equal to, so our lambda 1 is 7, 0, 0, and lambda 2 is 1, right? Now here, before I progress further and I show that this here is actually equal to this, before I show that, I want to say you something. That is, if, like, in case you did not choose your P to look like this, like instead of this you chose your P to look like CD and AB, that could also happen. So in that case it would be 1, 2, 1 minus 4. That's not wrong. You could choose this. You could make it like this. In that case, what will only change is the eigenvalues, right? So for this here, the eigenvalue is for this here the eigenvalue is 1, and for this here the eigenvalue is 7, right? So in the diagonalization, where you have here, if you focus in the diagonalization, only if you change this to, if you kept this here and you brought this here, in that case, the according to the eigenvectors, this would be 1 here and this would be 7 here. That's all it would change, but it's fine. You can do that way too. That's not wrong, right? It will still give you the right answer. Okay. Now that you know that, let's go ahead and solve this. So I'll first work on multiplying these two here. That will give me, okay, let me write this down. So here I have 2 over 6, 4 over 6, minus 1 over 6, and 1 over 6 times, if I multiply these two here, I get 7, 1, minus 28, 2, and that is equal to, we're saying 7001. So now if you multiply this here, you'll get, so 7 times 2 is 14 divided by 6, plus, so here minus into minus is plus, and 1 times 28 here, so 28 divided by 6 here. And then here we have for the second row times the first column. So here we have 4 times 7, that's 28 over 6, minus we have here minus 28 times 1 is minus 28 over 6. Alright, now again we go to the first row with the second column, so 2 over 6 plus minus 1 times 2, that's minus 2 over 6 here. And here we have second row, second column, so here we have 4 over 6 plus 1 times 2, that's 2 over 6, right? Now, if I solve this further, maybe I'll just, okay, let's keep it here. Okay, so that should be equal to 7001. Now here you have 14 over 6 plus 28 over 6, that would be 42 over 6, that's 7. And here this would cancel out to become 0. And here again 2 over 6 minus 2 over 6 is 0. And 4 over 6 plus 2 over 6 is 6 over 6. So that's 1. And as you can see here, we got it. We got our left hand side to be equal to the right hand side here, right? And we just showed that yes, the matrix A is diagonalizable because this condition holds true. And that's for today's tutorial. Thank you for attending.